So in this video, we're going to review functions. So let's start with an example. So let's talk about the daily snowfall in Syracuse, New York. This was recorded, we'll say, from December 15th, 2010 to December 5th, 2010 to December 16th, 2010. So this was recorded in the following table. So as follows. So let's give our table of this. So let's give the date and then the snowfall in inches. So we'll use these dates as the 5th, the 6th, the 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, and 16th. So we had 6.8 inches on the 5th, 12.2 inches on the 6th, 9.3 on the 7th, 14.9 on the 8th, 1.9 on the 9th, 0.1 on the 10th, 0 on the 11th, 0 on the 12th, 1.4 on the 13th, 5 inches on the 14th, 11.9 on the 16th, and 3.4 on the 17th. So note that for each date, we have a unique snowfall in inches. So for each date, we get exactly one measurement of snowfall. Right, so we can't say like on the 5th, 6.8 inches and 7.2 inches of snow fell. It was just 6.8 inches. So this tells us, since if we think of the dates as our inputs and the snowfall as our outputs, this gives us a function. Amount of snow as a function of the date. So you're probably used to seeing functions given by formulas, but that isn't always the case. We don't have to always have a formula. So let's go ahead and refresh our memory on what the definition of a function is, so we can see that this example above actually gives us a function. So a function is a rule that takes in certain numbers. Don't always have to be numbers, but for this, we're going to go ahead and say they're numbers as inputs and assigns to each input a unique output number. Again, the outputs don't have to be numbers, but for our purposes, we're going to require them to be numbers. So the collection of inputs is called the domain. And the collection of outputs is called the range. Okay, so hopefully we've seen these words before, but good to refresh them. So in our example above, we see our inputs are the dates. So our domain for above are just the dates: 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And then our output, the range, are just the various values that we can get for the snowfall. So if we order these in increasing order, notice they don't match up with the domain above. I'm just writing these in increasing order. These are the different possible snowfall values. And notice, even though 0 occurs twice, we only list it as once because this is just a set, so we don't need to list things more than once in a set. So it's 11.9, 12.2, and 14.9. Now, if we look above here, we see for each input, so each element of our domain, we assign a unique output number. So that does show us that this is a function. One other thing to keep in mind, though, is even though we have each input gives a unique output, we don't necessarily have that each output is only associated to one input. So note here that we can have the same output for different inputs. So each input only gives one output, but each output could be assigned to more than one input. Right, so for example, 11 and 12 both gave outputs of 0.0. So that's perfectly fine to have happen. Okay, so this is an example of a function that's just given by a table. A lot of times your functions, especially working with real-world examples, might be given by tables or by graphs. They don't necessarily have a nice formula associated to them. So we need to be comfortable working with all of the different ways a function can be given to us. Let's go ahead and look at another example. So let's say an object is put outside on a cold day at time t equals 0. So its temperature, say this is given by h equals f of t, and we're going to say this is measured in degrees Celsius, is given by the following graph. So here we're going to have t, which is measured in minutes. We're going to have h up here, which is measured in degrees Celsius. And then let's go ahead and draw a graph here. So let's say it looks something like this. So let's say this is up here at A, and this is down here at B. Okay, and this is the graph h equals f of t. So we can ask some questions about this. So for instance, let's interpret what this function actually means. So what does the statement say f of 30 equals 10 mean? Okay, so it's important for us to be able to take the math here and put it into everyday language. So this means we're inputting 30 as our input. So 30 is the input, and this is measured in minutes. And 10 is our output. This is in degrees Celsius. So what this is saying is if we go 30 minutes after 0, the temperature will be 10 degrees Celsius. So after 30 minutes outside, the temperature of the object is 10 degrees Celsius. So that's what that statement would mean. So let's explain what those numbers intercepts. So this point here would be 0a, and the other intercept would be b0. Let's explain what these mean. So if we look at our graph here, at 0a, that means our height, our temperature, is whatever a is, and that's 0 minutes outside. So the intercept zero a tells us the temperature of the object is a degrees Celsius when it is placed outside, right? Because it's placed outside when t is equal to 0, and that's where that a would be corresponding to. And now the intercept b0 is when the temperature is equal to 0, and b is now measured in minutes. So the intercept b0 tells us the temperature of the object is 0 degrees Celsius after b minutes. Okay. So it's really important that we're able to take graphs like this and functions and be able to read the information off of the graph. It's super important to be able to have that ability. We don't only want to be able to work with equations, we want to be able to interpret what graphs are telling us. Okay. So sometimes we'll also be given data that we can actually model with a function. Okay, so sometimes, and this isn't always easy to do, so a lot of times you'll have a computer model the data for you, but let's suppose we have a simple situation. So let's first say sometimes we may be given data that we want to model with a function. So given by an equation. And you'll see in actual applications, often there won't be one equation that fits all the data points nicely, so often you'll be looking for an equation that does the best job possible. But our example here is going to give one that models it really nicely. So let's maybe take an example here. And let's consider the winning height we're going to measure this in inches of the men's Olympic pole vault from 1900 to 1912. Okay, Olympics is only every 4 years, so we're not going to have a whole lot of data points here. So if we write these down in a table, you can look these up, and this was 130, this was 138, this is 146, and this was 154. So we can model this with the function, say y is equal to f of t, which is 130 plus 2t, where t is measured in years after 1900. So just to check this, note that if I plug these values in, f of 0, well, this is 130 plus 2 times 0, which is 130. F of 4, so this corresponds to 1900. This corresponds to 1904, so this is 130 plus 2 times 4, and this gives me 138. 1908, f of 8 is 130 plus 2 times 8, which is 146. And finally, 1912, this is given by f of 12, which is 130 times 2 times 12, which is 154. So you can see this function exactly models every data point that we have. Now, a natural question would be, does this continue? Well, you might guess without even checking, it's probably not going to, because you're probably not going to continue to go up by 8 inches every year forever. But we can just check the very next one. So in 1916, the winning height was 152 inches. So that clearly doesn't work, because it actually has gone down from 1912. So note, f of 16, which would be 1916 question mark, that's what it would be, we would expect, if our model was working, would be 2 times 16, which is 162. So the model stops working. Okay, so models usually aren't perfect, but that one gives us a little bit, our data for a little bit of time. So you might recognize this function is a particularly nice function. So this f of t equals 130 plus 2t. This is a line. Okay, so this has slope 2 and y-intercept 130. So to see what do these things actually mean, well, the y-intercept is when t is equal to 0. So that's just f of 0, which is 130 plus 2 times 0, which is 130. And the slope, this is the, often see this written as the rise over the run, or the change in the y values over the change in the t values in this case. You might have seen this as change in y over change in x, but in this case, our independent variable is t. So this should be given by f of t2 minus f of t1 over t2 minus t1. And so we can check this for any particular point. So for example, particular points, if I look at f of 8 minus f of 0 over 8 minus 0, this is 146 minus 130 over 8, and this is 2. And you can check any other points that you picked from our table up here, any 2 points, and you looked at the change in the heights divided by the change in the years, you would get 2 for all of those. Now in terms of the graph, what are these things telling us? Well, if I have t measured here in years since 1900, and the y here is measured in height and inches, then what our picture here will tell us is we see the y-intercept here is up here at 130. And then as we go across, it should be a line here, so something like this. So if we go over here at 4, 8, and 12, we know these values. So this point here, say, should be 4, 138. This point here is 8, 146. And the point here is 12 and 154. Now, of course, there aren't any actual values for the Olympics here in between these points. So for our actual data, we would just have the 4 dots. But since we're modeling it with the line, this line here is the function y is equal to f of t, which is 130 plus 2 times t. Notice if we wanted to just graph the Olympics data, we could do that as well. So the way we could think of this is, well, t and y, let's stay the same. And now let's graph our points. So we'd have this point here at 130, and we have one here, and one here. And so this is at 4, at 8, and at 12. And so this height here, this point is 4, 138. This one is 8, 146. And this one is 12, 154. So those are our actual data points. So let's fill those in with, those are dots. And so what we can really think of, what is the model actually doing here? It's actually trying to find an equation for a function that goes through these points. So that's what we actually did, is you would be thinking you're plotting those 4 points, and then you're trying to find a function that fits those as good as possible. In this case, we found one that fits it exactly. So maybe this is a good point to do a little bit of review on lines. So if we have a line given by this form. This is called slope-intercept form. And the reason we say that, because we have m here is the slope and b is the y-intercept. So in some cases, this is a nice form to work with. Other times, we'll want to use what's called point-slope form. The slope-intercept form is a special case of this. So in this case, if the line goes through a point, it doesn't have to be the intercept this time. So let's just say a point, call it P, and we'll call this x1, y1, and has slope m. The point slope form is given by, so we say y minus the y value equals m x minus the x value. So this is point slope form. So either way is fine. We can easily convert from this to intercept form. So to do that, just let's bring the y1 to the other side. So just add y1 to both sides, and then distribute the m through, and then just gather these terms. So I have mx plus, and then I have y1 minus mx1. So then this term here is the b, the y-intercept. So a little bit of algebra brings you back from point-slope form to slope-intercept form. Okay, so let's try another example. Okay, so let's say for tax purposes, you may have to the value of your assets. So we say an asset follows straight line depreciation if its value over time is a linear function. So just point out, I didn't choose this terminology. There's no reason to say straight line. All lines are straight. There's no other type of line. So probably linear appreciation would be a better term for this, but this is what it's called. So let's say, suppose you purchase a car for $50,000, and its value depreciates linearly to $0 over 25 years. Let's find a function, an equation for the value of the car as a function of t. Since we know it's a line, we'll be able to do this. Let's also ask, what are the domains? The domain and range of the function. Okay, so the first thing to know is we have two data points here. So if t is measured in our time, and let's say f of t is the value of the car in dollars, we know that at time 0, we have $50,000. Let's just say 50,000. And we know after 25 years, the value is 0. So that gives me 2 points on the line. So I can find the slope of the line by looking at the change in f over the change in t here. So I have 0 minus 50,000 over 25 minus 0. And so this is given by minus 2,000. And the units of this are the units of the top divided by the units of the bottom. So this is dollars per year. A lot of times it's very helpful to keep track of the units. It helps you interpret what's actually is meant by each value. So we also have the point 50,000 can be used as a point on the line. Also happens to be the intercept, but it doesn't so much matter. So then our equation for the line is y minus 0 is equal to minus 2,000. Using 50,000 for the value here. So y minus 50,000 equals minus 2,000 t minus 0. So solving for y, this is minus 2,000 t plus 50,000. Okay, so this here is my f of t. Now, the domain here is what can we plug in? Well, the values we're allowed to plug in are time can be at 0, and then it goes to 25, and then the value at that point of the car is 0. We don't want to go past that. It's not going to have a negative value. And the range, well, it can have a value of 0, and it can go until we get to 50,000. And if we'd like to graph this, this is just a line. In this case, we have t. This is measured in years. And this is y. This is measured in dollars. So this is going to start up here at 50,000. It's going to have a line that goes down until it's down here at 0 at 25. And this is given by y is equal to f of t, which is minus 2,000 t plus 50,000. So as a little practice with this, you can say, what does the statement f of 10 equals 30,000 mean? Well, we're inputting 10, so that's after 10 years, and we're outputting the value of the car. So this means after 10 years, the value of the car is $30,000. So a couple more definitions too that will come up that we'll need to remember. So the first one is we say y is, sometimes we'll just say proportional, sometimes we'll say directly proportional. So I'll put the directly in parentheses here to x. There's a non-zero constant. So that y is equal to k times x. Okay. Other things we'll use, we say y equals f of x is increasing if f of x1 is less than or equal to f of x2 for all x1 is less than x2, we say y equals f of x is strictly increasing. So strictly increasing is probably more what you're used to thinking of as increasing. If f of x1 is strictly less than f of x2, if x1 is less than x2. And then the same definition goes for decreasing. We say y equals f of x is decreasing if f of x1 is bigger than or equal to f of x2 for all x1 less than x2. We say y equals f of x is strictly decreasing if f of x1 is strictly bigger than f of x2 for all x1 less than x2. Okay, so let's have a few more examples here. So let's find a line through the points minus 2, 1 and 5, 6. So we have 2 points here. So first thing we can do is we can find the slope. So this can be 6 minus 1 over 5 minus 2. So this is 5, and then the negative becomes a positive, so 5/7. So we can use either point here. So let's use the first point and use point slope form. So y minus 1 is equal to 5/7, and I have x minus 2. So this is y minus 1 is equal to 5/7 x plus 2. So that gives us our line through that point. Let's try another couple more examples here. Let's find the slope and y-intercept of the line 2y plus 5x minus 8 equals 0. So when we see this line, we see it's not in either of our point intercept or our point slope form. So what we want to do is first we want to isolate the y. So the first thing we'll do is we'll take the 5x and the 8 and bring those to the other side. So I get a minus 5x plus 8. And now we want to get this y by itself, so we'll divide both sides by 2. So this will give me minus 5/2 plus 8 over 2, which is 4. And now from this we can read off the slope is the coefficient of x. So our slope is minus 5/2. And then this equation is in slope-intercept form, so we can see our intercept here is given by 4. Right, because this is in the form y equals mx plus b. Okay, let's do one more example. So the monthly charge for waste collection is, let's say it's $10 for 30 gallons of waste, and let's say $12 for 60 gallons. Okay, so let's start off, let's find a linear function. For the cost, let's say C, of waste collection. So that's our first step. So notice we have 2 points on our line. We have the point, if I have 30 gallons of waste, it costs me $10. And if I have 60 gallons of waste, it costs me $12. So then my slope here is 12 minus 10 over 60 minus 30, which is 2 over 30, which is 1 over 15. And so now my line, I can use either point here, so I'll use the first one. So solve this for y. So y is equal to 1 over 15, x minus 30 plus 10. So my cost function here in terms of x is 1 over 15, x minus 30 plus 10. Okay, so now let's interpret what the slope means. There's a couple of ways to phrase this. The main thing is our slope here is 1 over 15. And our units here are dollars per gallon. Right? Because the top part, the 12 and the 10, we're measuring dollars, and the 60 and the 30, we're measuring gallons. So we can interpret this a couple of ways. One way would be that if we increase 15 gallons more, for each 15 gallons more of waste, we're going to increase the cost by $1. So that's one way. So that would be one way to do it. The other way to think of it is maybe we don't want to have to increase by 15. We want to increase by just a gallon at a time. So in this case, we could say if we increase, so in this case, we can think of this as a 1 over 15 divided by 1. So that way we only increase the gallons by 1. So if we increase the waste by 1 gallon, the cost goes up by 1 over 15 in dollars. Okay, so hopefully this review of functions is helpful. And good, make sure when you're doing this, you're thinking of what do the functions mean, what does the slope of a line mean, how do I interpret things in terms of graphs and data and things like that, not just in terms of equations.